Hey, what's up, my chemistry people? Today we're going to start our new unit on equilibrium. As you take a look at our content objective for the day, we're going to explain the process of chemical equilibrium as a dynamic, reversible state in which rates of opposing processes are equal. All right, so let's break that down a little bit. First we're going to just identify just the fact that in many classes of reactions, we need to consider not only the forward reaction, but also the reverse reaction, which can be a bit of a mind shift for a couple of folks. We're going to define, interpret, and manipulate what is known as the equilibrium constant K. We are then going to express the equilibrium constant in terms of concentrations, known as Kc, or partial pressures, known as Kp, for reactions involving gaseous reactants and products, and then relate Kc and Kp to one another. So those are our big three things that we're going to pull away from today's video. So first things first, just some quick terminology here. When we talk about equilibrium, it's this sort of dynamic state in which we have to recognize that the reaction is happening not only in the forward direction, but also in the reverse direction. To indicate that dynamic forward and reverse process, we are going to use a double-headed arrow to indicate that reversibility of the reaction. And keep in mind that at equilibrium, both the forward and the reverse reaction are proceeding, so we have both reactants and products present at equilibrium. And so when you define equilibrium, it's this real dynamic state, and it's reached when both the forward and backward reactions continue at the same rate or the same speed, and the concentrations of the reactants and products are constant. Not necessarily the same, but they have a constant amount. So as we take a look at how we might interpret equilibrium in a graphical representation, you're given an equation there for the synthesis of HI from its elements hydrogen and iodine. And as you thoroughly study the graph, your reactants concentrations that you start with, as time progresses, they decrease. As time progresses, your product HI concentration will increase until we reach a point where the rates of both the production of the HI and the reformation of the elements hydrogen and iodine are occurring at the same rate. At that point, we consider what's called the reaction to be in dynamic equilibrium. Keep in mind that you can observe these graphical representations in a couple of different ways. In one type of reaction where the product is favored at equilibrium, you will note that you'll have a greater amount of product than you will reactant at equilibrium, or a reactant favored reaction where at equilibrium you're going to have a greater concentration of reactants than you do products. So just a couple of graphical interpretations there of equilibrium. Okay, now let's talk a little bit about the nitty-gritty, how we are going to quantitatively discuss equilibrium. We're going to use what's called the equilibrium constant K, which just relates to us the concentrations of reactants and products when the reaction has reached equilibrium at a given temperature. And as you take a look, the equilibrium constant expression K for that general reaction is expressed to there. Keep in mind that the product molar concentrations are in your numerator there. Your reactant molar concentrations are provided in the denominator there. And each concentration is raised to the power of its stoichiometric coefficient in the balanced chemical equation. So this is a little easier than your rate constant K. You can just pull directly from the balanced chemical equation to determine what those exponents are going to be, but it's products over reactants. Keep in mind, and this is really important, you should not include pure solids and pure liquids in the expression, as those concentrations don't change. This expression, the equilibrium constant K, is also known as the law of mass action. So you may hear that term thrown in and just recognize they're talking about the equilibrium constant K. Keep in mind that there are no units for the equilibrium constant K. They cancel out in this case. Again, a lot easier than your rate constant K, where we had to figure out the units for that. For the equilibrium constant K, they're going to cancel out. But now let's talk about what the equilibrium constant means. Okay, if K is greater than 1, the product formation is favored. Equilibrium concentrations of the products are. So you got a lot of product when K is greater than 1. As you take a look at your notes, you're given an example of a reaction that when it reaches equilibrium, there's a lot of product present. So notice as we look at how we describe the equilibrium constant K for this reaction, it's our products over our reactants. And as you look at sort of visually how that's represented at equilibrium, we've got a lot of these products formed. There are still some reactants, but a majority of what's in our container are products. And therefore, because products are in our numerator and reactants are in our denominator, we're going to have a large K value. So K is greater than 1, we're going to have a lot of product. As you look again sort of quantitatively how that works out, if you have a lot of product, again, a lot of numerator, your K value is going to be greater than 1. If K is less than 1, however, we say the reactant formation is favored. So when we hit equilibrium, there's a lot of reactants still left in our container. You're given a different reaction here in your notes to sort of describe a reaction in which the reactant formation is favored. So again, as this is written, it's products over reactants. But notice sort of as we look at the pictorial diagram of this reaction at equilibrium, there's a lot of reactants compared to our products. And so we're going to have a really large denominator here, and therefore our overall K value will be less than 1. Again, quantitatively, as you try to visualize this, when K is less than 1, you're going to have a lot of reactants at equilibrium. However, if K is equal to 1, the formation of reactants and products are equally favored. Essentially, you've got equal concentrations of both reactants and products.
Consider the chemical equilibrium between dinitrogen tetroxide, N2O4, a colorless gas, and nitrogen dioxide, NO2, a brown gas, at 25 degrees Celsius. Analysis of data for this equilibrium shows that although the ratio of the concentrations of NO2 to N2O4 gives scattered values, the ratio of the concentration of NO2 squared to the concentration of N2O4 gives a nearly constant value that averages 4.63 times 10 to the minus 3. K equals the concentration of NO2 squared divided by the concentration of N2O4, which equals 4.63 times 10 to the minus 3, where K is the equilibrium constant for the equilibrium at 25 degrees Celsius. Note that the exponent 2 for the NO2 concentration in this expression is the same as the stoichiometric coefficient. To convince yourself that the above equilibrium expression holds, no matter the starting concentrations, choose to start the reaction with pure NO2, pure N2O4, or a mixture of NO2 and N2O4.
Well, that was thrilling. Let's try it out.
Starting with 0.200 molar NO2, the reaction proceeds toward equilibrium, with NO2 molecules combining to form N2O4 molecules. At equilibrium, the concentration of NO2 is 0.0204 molar, and the concentration of N2O4 is 0.0898 molar. Calculating the equilibrium constant, K, we find K equals 4.63 times 10 to the minus 3. Recall that when chemical equilibrium has been reached, the reaction has not ceased. At equilibrium, the rates of the forward and reverse reactions are equal, and thus the concentrations of reactants and products remain constant.
Wow, that was really thrilling. Again, keep in mind a couple of things here. Macroscopically, the color to our eyeball here is mostly colorless, which was indicative of the N2O4 gas. So simply by looking at the color, we can tell which one there's a greater concentration of. And secondly, keep in mind our equilibrium constant K is really small, which is indicative of a large amount of reactant at our at equilibrium. And so our reactant in this case was the N2O4. Our equilibrium constant K is relatively small. Let's pick a different starting amount.
Starting with 0.670 molar N2O4,
All colorless.
the reaction proceeds toward equilibrium with some N2O4 molecules breaking apart to form NO2 molecules.
Slightly brownish.
At equilibrium, the concentration of NO2 is 0.0547 molar, and the concentration of N2O4 is 0.643 molar. Calculating the equilibrium constant, K, we find K
Oh my gosh,
equals
it's a constant.
4.65 times 10 to the minus 3. Recall that when chemical equilibrium has been reached, the reaction has not ceased.
No.
At equilibrium, the rates of the forward and reverse reactions are equal, and thus the concentrations of reactants and products remain constant.
And again, keep in mind it's dynamic. So we hit equilibrium. It's not like all of a sudden the reactions stop. It's just that they're proceeding at the forward and reverse reaction at the same rate. And so to our eye, it appears that they have stopped, but at the molecular level, they're still back and forth, but at the same rate. Should we do it one more time? I think so. It's going to be a really good one. Here we go. Mixture of NO2 and N2O4.
Starting with 0.430 molar NO2 and 0.300 molar N2O4, the reaction proceeds toward equilibrium with some NO2 molecules combining to form N2O4 molecules.
I wonder what the equilibrium constant
the concentration of NO2 is 0.0475 molar, and the concentration of N2O4 is 0.491 molar. Calculating the equilibrium constant, K, we find K equals 4.60 times 10 to the minus 3. Recall that when chemical equilibrium has been reached, the reaction has not ceased. At equilibrium, the rates of the forward and reverse reactions are equal, and thus the concentrations of reactants and products remain constant.
Wow, thrill a minute.